Here we look at the ring opening of an epoxide. We may recall that an epoxide is a three-membered ring containing oxygen, and we form an epoxide from the addition of something like MCPBA to an alkene. The result is an epoxide, this three-membered ring containing oxygen. And while epoxides by themselves may not have a lot of use due to the ring strain of the three-membered ring, turns out it's very, very easy to add nucleophiles to them, which forms an alcohol on one side and a new carbon nucleophile bond on the other side. Now, this reaction can be done under both acidic and basic conditions. And while in the past, there have been many reactions where we've said, we get essentially the same reaction, whether it's acidic or basic. In the case of the ring opening of an epoxide, that's no longer the case. In this first example that we showed, it didn't matter whether we were under acidic or basic conditions because our epoxide was symmetric. But as soon as our epoxide is no longer symmetric, like this one, just from the addition of a single methyl group, if we do this under acidic conditions, we find that the nucleophile generally adds at the more substituted carbon. And we can say that this reaction, this mechanism, is SN1-like. But if we do it under basic conditions, we get the opposite. The nucleophile adds at the more substituted carbon. So we could say that's SN2-like. So why do we get a difference here? Why is it so different whether we're under acidic or basic conditions? So let's start by looking at basic conditions. Let's say we add a nucleophile such as CN-. So under basic conditions, this is the SN2-like. The nucleophile wants to attack at the most accessible carbon, the least sterically hindered carbon, which is in most cases going to mean the less substituted carbon. Giving us this intermediate, which upon quenching with water gives us our product. So if this reaction is controlled by sterics, why is it then that using acidic conditions is going to reverse where the nucleophile goes? So when we add acid to many oxygen-containing functional groups, the first thing that often happens in these reactions is the lone pair on oxygen gets protonated. And that's because many reactions that happen under acidic conditions involve the use of weaker nucleophiles. And so if we're not able to protonate the carbonyl, our carbonyl does not get activated, and the nucleophiles are not strong enough to add. But we know that the oxygen-carbon bonds are polarized, and that oxygen wants electrons even more now that it's positively charged. So of the two carbons that it's attached to, which one's better able to donate electron density into the oxygen? It's the more substituted carbon, just as it would be if we were dealing with carbocations. And so because of that, when we add in a nucleophile under these conditions, such as water, it's going to prefer to add at the more substituted carbon, just like it would if we were dealing with an SN1 reaction. And then in a final step here, we'd lose a proton to get our product. But one of the very nice things about epoxide ring opening is not only is it a generally easy reaction to do because that epoxide is unstable from the ring strain, wants to open up, but in addition to that, we get very, very good control over the reaction, and in fact, we get, in many cases, complete control over where the nucleophile goes based on whether we use acidic or basic conditions.